Welcome to the second lecture on advanced algorithms. Here's where we stopped last time. We defined formally what NP-hard problems are, and we found that if a problem is NP-hard, then we probably have a problem, because unless P is NP, we cannot hope that it's solvable in polynomial time. Now, we stopped with the question if there are NP-hard problems in the first place. And as you know, of course there are. And, well, the mother of all NP-complete or NP-hard problems is the satisfiability problem. We've already talked about that informally. We have a set of formulas from propositional logic, so Boolean logic. And we have to encode these formulas in some formal language. And we don't want to be very specific about the details, how this encoding looks like. It should just be some reasonable encoding that doesn't waste exponential space or something like that. Apart from that, it could be just any natural encoding. And then we have the language of all encodings of all formulas that are satisfiable, where there is some assignment of the variables so that the whole formula is true. Now, why is that a good problem? Because it's NP complete, and it's maybe the only problem where it's kind of convenient to show that it is NP complete from the definition. So I think you probably have seen a proof of this. But still, I want to sketch a bit how it's done. At this point, it's very important that we have defined NP, the class NP, as with a specific computational model in mind, namely the Turing machines, the non-deterministic Turing machines. If you don't have such a model, then you're in trouble showing something here, because you have to say something about all problems in NP. But the first step towards the proof is to show that SAT is in NP. Let me pick this fine pen again. To show that SAT is in NP, it's convenient to recall that we have this class VP. That was the problems for which there is a verifier. And then the certificate for a formula that's satisfiable is just a satisfying assignment. And if we are given an assignment for all the variables, it's easy to evaluate the formula. You can basically do that even on a Turing machine. It's not so hard. Just insert the values one by time and evaluate Boolean operators and so on. Maybe how to do that very efficient is maybe interesting, but it's not interesting how to do it in polynomial time. So let me just say that the certificate for yes instances is a satisfying assignment. And the second claim is, of course, the more interesting one. We have to show that for any language in NP, that we can do the reduction. And at this point, we use that if a problem is in NP, then there's a non-deterministic Turing machine that solves the problem or accepts the language. And then we can use SAT to simulate the formula, to simulate the operation of the machine by a formula. And if you, well, recall this, so L in NP means there's a non-deterministic Turing machine that runs in polynomial time. I'm using the magic poly time again. And that means there's a specific polynomial, P, where again, we don't know how it looks in general, but we know that there is one. And then we can define a lot of variables, namely for the state of the Turing machine at time t. And we know that we need only polynomial time steps. Afterwards, it must have finished. Otherwise, we can ignore that run. It can't be accepting. we have the symbol in the input-output tape on the tape. And now add time t and position I. And again, we know that I only has a polynomial range. The machine can only ever move left and right by a single step, and if it only does p steps, then you can do minus p or plus p at most and nothing more. And again, you have to blow up by the alphabet size. For each symbol in the alphabet, you say, at time t, at position I find symbol A, yes or no. And then, what was the third thing? Now I forgot. Something else we need. The state, the symbol. I remember it was 3 bullets. Anyone remember? Well, whatever. So you combine a formula that mimics the transitions of the machine by setting certain or enforcing truth values of certain variables. And you include formulas that make sure that you only ever have one specific run that you simulate. And then in the end, the formula is satisfiable if there is one run that leads to a final state. Okay, so this is very sketchy. If you do it in detail, it's a few pages full of writing. It's not my point here to do that in detail. But maybe the sketch, and maybe if you do it in detail, you find out what the third bullet is. Maybe you can recall or imagine how the proof would look like. Now, once that we have a first NP-complete problem, it's easy to show NP-completeness for other problems because of transitivity. Whenever we show that a problem is even more complex than SAT, you know, recall that I said that this means more complex in ordering with respect to complexity in an informal sense, then also the new problem is NP-complete. And well, up to now I haven't mentioned many interesting problems. We've only talked about SAT, which is maybe not the most practical one at first sight. Many things are reduced to it. But here's a long list of other problems. We can restrict formulas to a certain normal form, conjunctive normal form, where you only have 3 literals per clause. You probably know that when there's a few graph problems, you can ask for a subset of vertices so that all edges in the graph have one of the endpoints in the chosen set. That's vertex cover. And we ask for such a cover of a maximal size. A similar thing is dominating set. We again have a graph and we pick vertices, but now for every vertices it is either itself in the set or one of its neighbors. It's a bit different, but also you may think about how to reduce one to the other. It's not extremely complicated. And again, we have a bound on the size of the set that we pick. Hamiltonian cycle is a bit different in that there's no such k in the input. You're just given a graph, and you ask whether there's a cycle containing all the nodes. And this is just a yes or no question, no parameter k. Then there's quite a few more. You have clique. Is there a clique of size k? It has a subset of nodes so that all of those are connected by an edge. Or the complement in a sense, independent set. Are there k, at least k vertices, so that there's no edges between any of the two? Traveling salesman is often formulated as a graph problem, but it's in the formal sense, it doesn't have to do with a graph. In this formulation, at least, you just have a matrix of distances and some bound, and you ask for a permutation of the numbers 1 to n, so that if you add up going from the ith to the next one, and the last step back to close the tour, does this total length of the tour be at most k? You ask for, is there such a tour? If you specify it on a graph, you can say it's a complete graph with these edge weights. And you can walk along the graph, which gives a nicer picture, but usually you assume that all edges exist. Another thing is graph coloring. You are given a graph and again such a threshold, and you ask for a coloring, C, that's a function that assigns labels to the nodes. And you require that any two nodes that are connected have different colors. You can think of the 4-color problem for coloring maps. That's a bit related, even though in a different setting. And again, this is another NP-complete problem. So maybe I didn't announce that before. All these problems are NP-complete. And for all these problems, you can use the transitivity of the ordering relation to show that. And many of those appear in practical applications over and over. Now here are a few more abstract problems that, for example, abstract from vertex cover. Set cover, you're given subsets of a certain universe, and you want to cover the universe by picking a subset of the subsets. Okay? Certain subset of the index sets so that you cover all the elements in the universe and you don't want to pick too many sets. You can weight the whole thing. You assign certain costs to the subsets. And now you ask, is there something where you don't exceed a cost bound? So the reduction between these two is easy in the one direction, right? Another thing, entirely different application in a sense, you're given strings all of the same length, and you ask for a string that's not too far away from any of the strings in Hamming distance. Hamming distance was you just sum all positions where the symbols disagree. So it's in bioinformatics they call it consensus string because it's a string that's close to these, and then you can imagine they vote on a consensus. Whatever. NP complete. Another classic one is max cat. So in a graph, you often are interested in min cats. You know that this is a much easier problem, but max cat, if you ask for a division of the nodes into one set C and all others, so that you want to maximize the number of edges that you cut by this partition. That's NP complete. And okay, this will be the last page. I'm just introducing them to give you a long list for reductions, to give you a sense for why NP is an interesting class. And also, I think I only included problems that appear somewhere in the lecture again. So that might give you a reference for notation. I hope I will stick to that. Subset sum is a very simple problem. It's maybe interesting for that respect because it's just a few numbers and you ask for, is there a subset of those that sum to 0? That sounds very simple, but NP complete. 0-1 knapsack, a problem that we might reconsider later in the lecture today. You're given n objects that have weights and values and certain bounds again, and you ask whether you can find a subset that doesn't weigh too much but gives you a lot of value. Bin packing is a bit similar. You have again weights, and you want to assign each object to a bin. That's why you assign each of the n objects to one of k bins, so that none of the bins is over full. Each bin has size b, and you want to fit at most weight b to each bin. Lastly, maybe the most abstract one of this list is you're given just a bunch of numbers, matrices and vectors, and you ask this only algebraic question, if you like. Is there some vectors so that this set of inequalities is satisfied? So this is matrix vector product, of course, and here scalar product, if you like. And in terms of optimization problem, you want to maximize this term subject to this side condition. And here again, instead of maximizing, we're picking a threshold. Okay, that was a long list of problems. Before you start yawning too much, I'll stop here. This is definitely not a complete list, but we won't cover many more problems in this class. Now you might have noticed that a lot of these problems have such a parameter k here that was kind of a threshold. So we didn't want to go above or below a certain threshold, and the reason is that for many of these problems there's a natural optimization version. We already talked about different versions of the same problem last time, where I said we have a decision problem on the one hand and we have a certificate search problem on the other hand. Now here's a few more versions that we will discover. And for example, let's take bin packing because that's still on the slide. If you drop the parameter k and just ask what's the smallest k so that you can fit all objects into the bins, you get an optimization problem. I guess that's easy and natural enough. And the question is, can we say something about optimization problems in terms of our NP theory? At first, it might seem that the answer is kind of no, because it's not a decision problem, right? But we can easily transform it into one. Nevertheless, I want to give a formal definition of what optimization problems are, just to demarcate what maybe is not a valid problem. Okay, TCS again. We're defining tuples. An optimization problem is such a beast, where we have input and output alphabet, because now we're not just outputting yes or no, but we output a solution to the problem. Now the first thing that's maybe not so trivial is, why do we have L and Li? The first thing is all allowable instances that make sense in the application, if you like. So that might be all encodings of a graph. But in the actual problem that you're considering, you further restrict that set of allowable instances. Maybe for that purpose, you're only looking at planar graphs, because you want to see if TSP is still NP-complete on planar graphs. Okay? And then it's sometimes convenient to just have this distinction. I think it's a technicality. Then for any instance, you have a set of feasible solutions. So for any fixed instance, m of x is still a set. And that's all feasible solutions that respect the side conditions. And any of these solutions together, so an instance plus one of these solutions, or the other way around, that's the solution, that's the instance. They together have a cost or a value, which is just some number. And then you can also specify whether you want to find the smallest or largest of such values over all feasible instances. I'll talk about this real number here in a second again, but for the general setting, we can just allow that. It's just the definition of a problem. It's not anything about computability up to now. If we have problems, we should also have algorithms. So if this is one such optimization problem, then we say an instance and a solution that's feasible for this instance is optimal for this instance. Well, if the cost of these two is just the best that you can get in that setting, which means inserting min or max, whatever it is. And then here you have all feasible instances for that instance, feasible solutions for that instance. Okay. Probably natural. An algorithm then has to be such that it computes an optimal instance, but it must also always return something that's in the feasible set. Otherwise, you could maybe do kind of nonsense. It's not a very surprising definition. Okay. We've seen a lot of examples of optimization problems, even though I didn't formulate them as such. If you go back in the slides, then you can see that whenever I use the parameter k, this is actually something that turns into the optimization value. I think most of the problems actually have this. Another example that's maybe a bit less natural, but because SAT is the mother of all NP-complete problems, we should also have an optimization problem for SAT. And we can define max SAT, at least for all formulas in conjunctive normal form. So we have a formula that's formed as a conjunction of clauses. Now the allowable instances are just all encodings of such formulas. And again, I don't want to go into detail of the encoding, but probably you can just name the variables by their number and specify whether they are negated or not, and then you have a list of these things, a multi-set of these things. The feasible solutions for a formula are just variable assignments, or assignments for the n variables to true and false. The cost, now this is the first thing that we really have to define. I think up to now it's easy that this is the way to go. Now we want to maximize, goal is maximize the number of clauses that are fulfilled under a given assignment. So the cost is the number of clauses that are fulfilled. Okay. Of course, if we fulfill all clauses, then so if max cost, it would be nicer if that was just called value, but that's how people get used to it. If this is m in a certain instance, so all clauses, then of course the whole formula is satisfiable. So it's easy to see that this generalizes the ordinary SAT problem on CNF formulas. Okay. Now to the more interesting stuff. What's complexity classes for optimization problems? First, we'll look at NPO, so the equivalent of NP, of course. And an optimization problem is in this class. First of all, if I can decide in poly time that an instance is feasible, is allowable for this problem. So this is not only the L, it's the Li. So I need a checker to see whether this is an input I should treat at all. It's clear that we need something like that. Also, the cost function should be computed in polynomial time. Otherwise, it would be a pretty strange conception of cost. So this means that we essentially only need to output the solution and not its costs, because we can always compute the cost from the solution. And then the remaining requirement is for any instance of the problem x, we require that all the possible feasible solutions for this instance are bounded in length by a polynomial. This is also required because if we couldn't even write down the solution that we should output in polynomial time, we can't find reasonable algorithms. So this is a bit more than, so it might be that x can be concisely encoded, but still allow very large solutions. So we have to explicitly forbid that. And then this only says for all feasible solutions we have a bound. We also should be able to check whether a solution given to us is feasible in polynomial time. Okay? This is just, if you think about it, this is what you need to require to talk sensibly about these kind of problems. And, well, it's not surprising, but I think it makes sense to once write it down and make clear what is behind it. Okay, at this point, we might add that if this cost function should be computed in poly time, we can't really deal with real numbers. So at this point, it makes sense that we only consider integral cost functions. So in principle, you could be a bit more flexible and allow maybe rational numbers or something. But then, again, you could, for all the instances, just multiply through with the common denominator, and usually the numbers shouldn't explode too much. Or you work with some fixed precision representation of reals if you insist on these. But if you go back to the problems that I listed, in all of them I just defined everything in terms of integers, and there was no instance where I thought that this would be very unnatural. So let's, for this course, stick to integer costs. There will be, in a few weeks, one point where this really makes a difference. Then I'll remind you of this convention again. Okay. Now this was the class NPO. Oh, we might argue that our nice problem maxsat is actually an NPO. What we have to show is the 3 points, of course. Now we should be able to recognize encodings of formulas that's the same as before. So if we buy that, we did that before for sat, we can also do it for maxsat. The feasible solutions for such a formula were the variable assignments, and sure, if a formula has a certain length x, then this is also an upper bound for n, the number of variables, and that's the length of the solution. So we certainly have the first part. It's even linear in the input instance length. Well, and I already claimed at least the second part. Given a formula and an assignment, we can check in poly time whether the formula is fulfilled. And that's not the part, sorry, that was the cost. We can parse whether this is a valid binary vector. Well, there's not much to do. Okay, B is even easier. And the cost is what I just said. We have to evaluate the formula clause by clause and sum up how many are fulfilled. That's also easy. Okay? And as you see in this case, often it's even natural to have integer costs if you count things. That was NPO. Now what's the class of efficiently solvable optimization problems? That's PO. And we require first that the problem is an NPO, and there's on top of that an algorithm that really computes, given an instance, an optimal solution for the instance in poly time. That's quite naturally what we would like. It just solves the problem in poly time. Now at this point, we might I'll start a new page. We might add a remark on problem types. Last time I already started our glossary of problem types. Now we extend it again. So we already had decision problems and search problems, where decision problem was just a yes-no question, whereas the search problem was phrased as the decision problem. But instead of only yes-no, if the answer was yes, I wanted to see a proof, a certificate. So both were in the setting that we check whether the optimal value is below or above a certain threshold. If we consider these as specific versions of optimization problems, then we get a threshold and we check whether it's solvable with that threshold, yes or no? And if so, we want to see proof, that is, an instance that achieves this cost. So this was, we only give a single answer, yes, no. Or here we want to see the solution or a witness for the yes. Now for optimization problems, we also have the more natural formulation asks for the optimal value itself. So the most general thing here was the optimization problems as we just defined them. You wanted a solution that has optimal value. And the third thing also has a name that's sometimes convenient. It's the evaluation problem. There you're only interested in the optimal objective value, the optimal value of the objective function that you minimize or maximize, but you're not required to output a solution. All these problems are a bit different, and the complexities might also be different, right? In general, we should be a bit concerned. But there's a few easy directions. Going from bottom to the top row is relatively easy because we assumed that goal is computable efficiently, right? Cost, sorry. So this is sloppy because P is decision problems, but we can compute costs. So if we have this, we can compute this. If we have a search problem, well, if we have a certificate, we can check it in polynomial time. That was VP. So this is easy. It's also easy to go from right to left. All we have to do is, given that optimal value compared with the threshold, that's even easier. But the other directions of these arrows are a bit more interesting. That was completely bogus, sorry. Oh no. Confused myself. What's the other directions? So if we want to go from top down, that's from decision to search. That's something we talked about briefly last time already. It's often easily doable, as you will show in the exercises. But in general, it's not so clear. So if you recall, for every decision problem, we can have this kind of canonical certificate that corresponds to the decisions of the non-deterministic Turing machine. But the string of these decisions does not necessarily have a meaning for the application. So you might have some non-deterministic machine that decides SAT without giving you the assignment explicitly. Hard to imagine, and for the SAT problem, you'll show that you actually don't have this situation, but it's hard to show in general. Now the new thing is from left to right. You have the threshold, and you want to get the optimal value. Here it's important that the cost function is integral a bit. It's already a bit important. Could circumvent it, but you essentially can use a binary search as long as the range of possible outcomes for the cost function is not too large, and it can be pretty large. So binary search takes the logarithm of this range, and that's something that has to be polynomial. So the largest allowable value would be 2 to a polynomial. That's already quite a lot. And in fact, you can't even output more bits by a cost for a cost function. If it's computable in polynomial time, the number of bits the number has must be polynomial. So this always works for costs in n. So it is essentially sufficient to consider the simplest of these problems, namely the decision problems. It's not fully resolved, as I said, because going top-down is not always so easy. But what we said here in terms of decision and search problems is also true for evaluation and optimization problems. You can think about it as essentially two sides of the coin. So for the most specific problems, it's easy. And if you find out that the decision problem is easy, usually also the others are easy. And for the other direction, if the decision problem is hard, we will show that the others can be easier. That's because of the reductions here. Okay. Yeah. So we restrict our attention to decision problems, to the decision version of optimization problems. And the formal setting to do that is a threshold language. If you have an optimization problem, we will always call, so if you use the problem opt_u of an instance is the optimal value, so the result of the evaluation problem. And then we define threshold languages written as lang_u. That's a word that consists of two parts, an input instance, an encoding for an input instance, and the encoding for a number. So K2 here just means the number represented by this binary string. Maybe a bit over-formalized, but we are always talking about words in the formal setting. And now you make a distinction between min and max because you have to reverse the direction, otherwise the problem becomes boring. And now we call an optimization problem NP-hard if the decision the threshold language, so its decision version is NP-hard in the sense we defined before. So we just extended the notion of NP-hardness to this more general class by this vehicle. Okay. This is what I already said. I want to briefly give a proof in the formal setting. If the threshold language is NP-hard in the usual sense, then U will probably not be in this class PO of efficiently optimizable problems, efficiently solvable optimization problems. Now for the proof, assume the contrary, assume that U is in PO. So that means there's a polytime algorithm for optimizing this problem. Let's call it A. So that computes an optimal solution Y for any instance X. Let's just write X in U instead of these languages and so on. So that means we can solve the evaluation problem, right? If we have the instance, we can compute the cost. So opt_u can be computed in polytime. Well, and then we only have to check opt_u of X less or equal or greater equal, depending on the goal, then a certain threshold can be computed in poly time. And that means that we have a poly time algorithm for the language lang U. But since that was NP-hard, and the lemma before, that would mean that P is NP, and we assumed that it's not. So intuitively, it's just the steps that I showed in the as arrows before. Let's again see a specific example with our tried and trusted max set. So to show that it's NP-hard, we don't even have to show anything. We already showed that it's in NPO, but we haven't generalized the notion of NP-complete to optimization problems. It's not part of the formal definitions. Maybe it should, well, if you want to have it, you would require is in NPO and is NP-hard. So what we want to show is that C and F set, or maybe 3 set, is easier than lang max set. So the theorem of Cook and Levin, by the way, these two guys independently found the proof for set is NP-complete, and they also independently found this notion of NP-completeness, I think, which is interesting, but only a few years apart from each other. Well, 2 years, okay. Well, Cook was a bit earlier, so often it's only called Cook's theorem. Maybe that's not fair. 2 years is not so much, given that journals sometimes need more time to publish a paper. Okay. We only showed that the general version of SAT is NP-complete, but we had one of the problems, 3 SAT. 3 SAT always has formulas in conjunctive normal form. That's also NP-complete, even though we didn't prove it. So we can start with that and just reduce any of these formulas to max SAT, to the threshold language. So if X is an encoding of a formula phi in conjunctive normal form, and say it has M clauses, you can guess how we set the threshold now. Let me say compute even in quotation marks. You compute this tuple and check whether it is in lang max set. And that's the reduction. If it is, that means that all M clauses are satisfiable. If it's not, that means the whole formula is not satisfiable. Because that was, the language was just the instances so that we have M or more clauses satisfiable. And since there are only M, that means exactly M or all. Easy enough. Okay, so that completes the first part of the lecture in the first chapter, where we just basically recapitulated notions from the theory of NP and P and NP completeness. We have seen some formal definitions of all these terms that we had. We thought about what running time is, and especially what poly time means, because we want to abstract from a lot of things in this lecture. We've seen that it's convenient to work with formal languages which correspond to decision problems. And that can be used to define complexity classes P and NP. We've seen these two equivalent definitions, where depending on the use case, one or the other was more convenient. And we've seen that problems arising in practice are usually optimization problems, or many are optimization problems, and sometimes others can be cast into this form, like for satisfiability. And there's 4 different versions of the problem. And we can avoid dealing with all of them. Mostly in terms of complexity, it's the decision problem that decides whether it's hard or easy. But if you really implement things, then it's often a bit more work to unravel all these steps. Okay. So in a sense, we found that we can mathematically prove that a problem is hard. But the actual goal of the lecture was to say, what can we do in this case? What can we do if a problem is hard? And the first idea that we can use is pseudopolynomial algorithms that are sometimes efficient, even in practice, and are often confusing for beginners in theory. So that's a good topic to start. And also because it provides an entry to fixed parameter tractability. As I mentioned in the first lecture, you can say this max in that we will discuss in a second is a parameter. The theory of pseudopolynomial algorithms has to restrict problems a bit, namely to those, I'll just call them integer input problems. It's not a coined term that I found somewhere. People are often a bit sloppy about specifying what exactly is the set of problems to which this theory applies. But we need something that's just consisting of integers. It's not really a severe restriction because, as you know, you can encode virtually anything as an integer if you like, but not always is such an encoding meaningful. So we will in the following just assume that instances consist only of a sequence of integers. Then for any such instance, we can define maxint, which is just the value of the largest integer occurring there. And since we encode integers in binary, the encoding length might be pretty small, even though maxint can be large, exponentially larger. That's all easy stuff, I guess. I mentioned that we can cast all problems in this form if we like to, but there's also a list of problems that we've seen before that are naturally sequences of integers. So examples would be traveling salesman or salesperson, the knapsack problem, same for bin packing, which is a bit similar, and also this very general integer linear programming is also just involving numbers. And well, if you know about that a bit, then you can cast a lot of problems into ILPs, and then you can apply the theory here if you find a pseudopolynomial algorithm for general ILP. Good luck with that. Okay. I've already talked about pseudopolynomial algorithms. Now I want to be precise about what that means. We have such a problem as we just defined it, only consisting of integers, and an algorithm that solves it. Now we call this algorithm pseudopolynomial if it is indeed, its running time is indeed bounded by a polynomial, but one that doesn't only take the encoding length of the instance, but also maxint. And to reiterate, this might be much larger. So a trivial observation is if this is not much larger, but only bounded by some polynomial h, then the whole thing is a polynomial, and then we have a polytime algorithm. If this is not true, then the algorithm is not so efficient. Oh, nice. So here the slides are over. I don't see why. Okay, now the history is gone, but I'll cut and paste it together for you. So we've talked about pseudopolynomial algorithms. We found that if maxint is indeed bounded by a polynomial, then we have a good algorithm. So it makes sense to define such a thing. The value-bounded subproblem of some integer input problem has a parameter h, that's just some function. And we say, we define a new problem, value h of u, that consists of all instances where the maxint is bounded by h of the input's encoding length. Okay? And, well, as we just discussed, for any polynomial h, if we have a pseudopolynomial algorithm for the problem u, we have a polytime algorithm for value h of u for any polynomial h. This is, well, I wrote it down, maybe let's give a quick proof, even if it's relatively simple. So pseudopolynomial means means that there's this algorithm A that runs in time O of a polynomial P, length of the input, largest integer in the input. And we assume that for our restricted problem, where h is a polynomial, we have the bound on maxint. Oh, sorry, h. And since h is a polynomial, this is bounded by some x to the c for some constant c, whatever it is. And that means we can just compute what we have here. The maxint is, okay, let's directly go to O. Insert here. And then the polynomial where you insert x to the c for the variable remains a polynomial with a higher degree. I mean, just by inserting it's clear. That's for some d. That's a bit larger depending on the degree of h. So this is again a polynomial, so A has polytime. Okay, I should just save it somehow. Now let's see this in action on a real problem. Considering the knapsack problem. So we've already seen the decision version, but here is the optimization version once more in case you don't remember. We have a collection of n items given by their weights. That's how much they contribute to the weight of the knapsack, which is bounded by b. and they also have a value, which is what we want to maximize. So the total cost here, cost in the terms of an optimization problem, but it's actually a profit, is the sum of these VIs that we pick, but we must obey the constraint of the knapsack. They cannot weigh more than B. Now, how shall we solve this problem by dynamic programming? So the idea will be to compute smaller problems many times. And the key idea is that the ith item can be taken or not. Essentially independently of the rest. But we have to make sure it's not too heavy. So in total we have to respect the weight bound. But still, in a sense, it's only the total weight of all other items that we pick and the total value of all other items that we pick that has an influence on the decision whether we pick the ith item or not. But still, the problem is, how shall we decide whether we should pick it or not? So to ease that decision, we also fix the exact profit that we want to hit. So we specify the profit k, and we want to precisely pick objects of that profit, of that total profit. And if we do that for all possible values of k between 0 and v, which is just summing over all items the value, then we are sure that our optimal solution will be one that has in the end the profit k for some of these values. And here you sum values of the input, not lengths of encoding, so this will be where pseudopolynomiality comes in. Now, as typical for dynamic programming, we fill a large matrix, and here the matrix is given an integer I and this profit bound, this profit target k. We're only allowing to pick items up to index I. That's how we will in the end get a recurrence. And the value at this position is simply the best weight that I can reach for any such collection of objects. So it's a weight so that we find a subset of the first I items that sum exactly to this given value. That's W, which must be smaller than B. And also we have the constraint that the sum of their values is exactly k. So this is the important part that will make the recurrence easier. Namely like this. We can compute by making I smaller. We essentially have two options for the ith element. We can either not pick it, so don't pick I. That means we still have to reach profit k, but we're considering less elements. The other option is that we pick the ith element. That means the others only have to sum in value up to k minus vi. but then the weight that I get is plus wi. That corresponds to the choice of picking I. Now the initial values, if we go down, then at some point I is 1. And here we actually have 3 different possibilities. If we target at no profit at all, we just pick nothing, that's fine. If we exactly by chance or whatever have the profit goal of V1, then we can exactly pick that single object. And in all other cases, we set this formally to plus infinity because there is no collection of objects that consists only of a subset of the first object that sum to exactly that profit. There's simply no possibility to do that. And then in the recurrence, this will make sure the plus infinity that we never use a subproblem that's actually not possible to solve. So I guess it's clear that we can compute these bottom up. Now the final solution in the end is just with all objects that we have. And for the k, we start with k equals v, and then just go down. Until this value a and k is not infinity. So that means until we found a profit that's actually attainable, and then we have a non-infinity value here, and that's also the weight of the optimal solution. And well, the actual optimal choice of items is easily found by backtracing through the recurrence. That's the ordinary backtracing step in dynamic programming. So if you, for instance, for the last step here, you have a certain k, then you can check which of these two options for n-1 as I gives this value that you found there, and then that tells you whether you should include in the optimal solution the nth object or not. And then you go back like this through the matrix. That makes it a bit easier. You could also try to just collect the set of objects on the fly, but it's needs more space and doesn't really, and makes the recurrence a bit more messy and doesn't buy you much. Now let's quickly analyze the running time of this thing. The essential point is to count the number of items that we have to, or the number of entries in this matrix that we have to compute. And so for the first component, we simply have n, the number of items. For the second, we have v, because that's all feasible values for k. For smaller I, we could actually make it a bit smaller, but well, we don't know up front. No, it's not. Nothing is really possible. So that's the number of entries that we have. Now, v itself is not exactly max int, largest integer in the input, but we know it can't be more than n times max int, because it's the sum of n integers, and each is from the input, so each is bounded by max int. So this is actually n squared max int, never more, which is a polynomial in the 2, right? Now the running time of the algorithm is actually a slight bit more, because where we have here So this is the number of entries, the time to compute one entry. It's O of 1 in the uniform model. But here we have to deal with numbers in the recurrence that might get large. So if you like, you should say it's logarithmic in max int. Which is still, if you multiply it with this, then it's still bounded by a polynomial in n in max int. So overall, we've still shown that this dynamic programming algorithm for the knapsack problem is pseudopolynomial. So maybe log factor missing. In the logarithmic model, but it doesn't make any difference for the statement of the theorem. Now this was a nice example. We might be hoping that we can find such an algorithm for all problems. That would already be good, because for at least certain instances this is fast enough. It's polynomial for the bounded subproblems. But there's also a hardness result that tells us this is not going to work for all problems. Namely, we can refine the notion of NP-hardness and make it strong NP-hard. If we find a polynomial p, any such, so that the restricted problem is also NP-hard. So even if you have only small numbers, the problem is still NP-hard. Now Knapsack is probably not such a problem, but even though our algorithm was pseudopolynomial, we haven't yet shown that there's not another polynomial so that the problem remains hard. Since our polynomial is so small, it's hard to imagine. And we'll see in a second a bit more on that. But the definition, first of all, is it's strong NP-hard if there is any polynomial so that the value problem is hard. Now, if a problem is strongly NP-hard, then we will not have a pseudopolynomial algorithm. That's the last thing that we are proving today. So the formal statement is unless P is NP, if U is strong NP-hard, then we will not find a pseudopolynomial algorithm. So let's let U be strong NP-hard. By the definition, that meant that there is some polynomial P, so that the restricted subproblem is NP-hard. Well, but we've already seen that if there was a pseudopolynomial algorithm, for the problem U, then A runs in polytime for all instances of the restricted subproblem. Should have written down the number. Okay, I'll replace it by the number if you like. It's not so far ago. There you go. 2, 4. It was a theorem, not a lemma. My bad. Yeah, if you're used to LaTeX, then you don't remember theorem numbers. They're changing anyway all the time. Okay, where was I? So then this runs in polynomial time. Well, and then we have and this is, okay, sorry though, that was the confusion. This is for any polynomial q. Well, and then in particular for our polynomial p. But we've assumed that this is NP-hard. So that'd imply that P is NP, and we assumed it's not. The usual kind of argument. So the good thing about this is whenever you find a single polynomial P where this value restricted subproblem is hard, you already know that the search for pseudopolynomial algorithms is useless. So that essentially found that for any value, for any polynomial q, this is also NP-hard. And there's a simple example where this polynomial is extremely small. Strongly NP-hard. I think I can squeeze it into 2 minutes or so. We've already defined the TSP problem above. I think you have it still in mind. It's essentially given by this distance matrix. And you ask for a round of visiting all the numbers 1 to n and counting the total distance of the tour. And you also recall the problem Hamiltonian cycle. That's usually used to show that TSP is hard. So we can just make that reduction with a bit care to the numbers, and then we'll see that it suffices to show that TSP is strong NP-hard. So we show this essentially, so this should be a function, so it's just a constant. I claim that you can use just constant costs in TSP and still have an NP-hard problem. And the idea is, if you're given a graph for the Hamilton problem, and it has a certain number of edges. Other edges are not present. And you just make all these edges have weight 1. And all the non-edges that are not there in the original graph get distance 2. So it's already for the small problem, there's a lot of non-edges. I won't draw all of them. Now this is your instance for the TSP problem, the distance matrix where you have only entries 1 and 2. If the original graph had a Hamiltonian cycle, it of course only used 1 edges because there are only 1 edges. So the total cost of a Hamiltonian cycle would be just n, the number of nodes. If it has a Hamiltonian cycle, then there's a tour of length exactly n. And this is actually an if and only if, because every tour of length n that uses n hops can only use edges of weight 1. If there was a single 2 edge, it would already be over. So it's exactly if and only if. And we know that Hamilton is NP-hard. So these two together show that already this very restricted version of TSP is NP-hard. So TSP is strong NP-hard, and we won't find a pseudopolynomial algorithm for it. That already completes the chapter on pseudopolynomiality, because there's not so much more to say about the topic. But as I said, it will be the motivation for a much larger and a bit more novel topic for you, hopefully, on fixed parameter algorithms. That we will start next time.